Yeah, that's fine. Morning, everybody. Hope everybody had a good time last night. See some groggy faces out there. So this is Return from the Underworld, the future of Red Team Kerberos. My name's Jim Shaver.
My name is Mitchell Hennigan. Do pen testing in Red Team.
Absolutely, we're with Crow Horwath. Today we are going to talk about Kerberos, the future of Kerberos and AD. And we're going to start off with a little bit of a review for those of you who want it. We're going to talk about how Kerberos works. We're going to talk about one specific attack called Kerberoast, talked about earlier yesterday a couple times. We're going to talk about some attacks and tools. We're going to talk about the future of password cracking within Active Directory and go over a little bit of how Kerberos key generation works, as well as releasing a brand new type of password cracker. And we're also going to talk about the future of this specific attack, Kerberoast, and whether or not you can actually disable RC4, what are some of the ramifications around that. And finally, we're going to talk about the future of AES and NTLM within Active Directory. And one of the reasons that we did this talk is there are plenty of people out there who, you know, if you were in a room with a CIO or a CISO, you would be comfortable talking about like basic authentication or, you know, NTLM authentication or something else. The comfort in the security community and the IT community around Kerberos is not great, right? So one of the goals with our presentation is to help you strengthen your understanding as an attacker, but also, you know, as a defender around Kerberos. So how does Kerberos work? And most people in the I will paraphrase the immortal words of Shaggy 2 Dope. You know, most people have seen a slide like this or an image like this, and this is the fundamentals of how Kerberos works. There's 3 stages. Each stage has a request and a reply. The AS is the first authentication that the user does, where they trade in their password for a hardened token that is you know, has a lot less attack surface. And then every time that a computer or a user authenticates against a service within Kerberos, it does this second and third stage of the authentication. The TGS, where it actually talks to the domain controller and says, hey, I'd like to authenticate against something. The domain controller actually, and we highlight this in this picture, hands it back an encrypted ticket that the client then hands off to the service that it is authenticating against. Okay? And this ticket is important, and we'll explain a little bit why. Next up, one of the things that we did in researching this talk, and one thing that's really valuable, is actually looking at Kerberos with Wireshark. It gives you a lot of information about how Kerberos works and actually lays out things in a pretty logical way. This is, for example, the way the TGS reply is laid out in Wireshark, and that ticket section encrypted with the services key, that's the ticket that we saw on the previous slide. The other interesting, important aspect of Kerberos are service principal names, okay? Now, service principal names, if you're familiar with them, you understand that this is a Kerberos registry that maps services to the accounts that they are running as. The reason, and this can be a user account or a computer account, and this is maintained in Active Directory within LDAP attributes. And the reason that the DC maintains this is because it needs to know how to encrypt that special ticket when sending it to the client to send on to the service. One interesting thing to keep in mind is that most tools that we use actually filter out computer accounts, because most of the attacks make it far too difficult to crack these computer accounts' passwords, and so it just doesn't want you spending any time on something that's really difficult. But it's good to keep in mind that every computer joined to a domain actually has a service principal name. It is another form of enumeration that you can do. If you have authentication, you can pretty easily gather all of the hosts in a domain. They may not be accurate, but that's another question. So next up, how are these SPNs created? So one example is when a computer is joined to the domain. Other examples are when services are installed or software is installed, it will publish attributes into the account that the service is running as. And this isn't just for Microsoft software. There's a whole list of third-party software that does support this, from Dell and names you are familiar with.
Yep. So the next part, after really setting the base of really how Kerberos works, is to talk a little bit of the actual attacks that have been again presented here about 2 years ago as far as Kerberoast works. So really the main question here is how does it work? So Kerberoast really doesn't do any invalid requests. It's legitimate traffic. But the real problem it comes down to is two things: weak passwords and old crypto. But the way it works is it essentially just goes through the list, requests all the tickets it can, and then that's what you're actually going to come back and then try to crack later. So doesn't require a lot of auth, just basic user auth most of the time. And then it does allow you to kind of bounce from domain user to DA really quick most of the time, because you need to run services as DA. That just makes sense. So at the bottom here is kind of just an excerpt from the first part saying, okay, here's the initial auth, but then that last part where I actually forward the ticket onto the server, it just kind of ignores that. Since we don't actually need to authenticate, we just need that ticket. So the next part here is another screenshot really from Impacket. So I just kind of wanted to bring everyone up to speed kind of along with us on what we discovered while looking through Impacket. So the way Impacket really works is you authenticate, and then once you're authenticated, you actually pull all the SPNs out of those 80 attributes that you previously pulled. So it goes down the list and says, does this user have an associated SPN? And then basically goes through the list and says, okay, I'm going to request tickets for every single one of these accounts. And then at the bottom there, you can see that's actually what you're going to throw into Hashcat, any sort of tool like that, and actually try to force to actually crack those tickets. Now, since we are pulling from LDAP accounts, these are going to be user accounts. So it's going to filter out all the machine accounts, which we're really not going to crack anyways. And then another benefit here, which we'll talk to later, is really that all these tickets are going to be RC4. So very old crypto, and then that just makes them that much easier to crack. So that's really the fancy hacker way of doing it. There's a more native way using PowerShell and Wireshark. So one of the things you can do with Wireshark actually is to actually generate a key tab, which is kind of just a key hash table exported from the DC, and then you can basically actually start decrypting these Kerberos packets within Wireshark. So now while that sounds cool, you're really not going to get much. What it lets you see is really going to be some of the nonsense, some of the just kind of the negotiation that goes back and forth between the service and the domain controller. So not a whole bunch, but it does kind of let you peek in a little bit as far as what's actually in those tickets. But this is how the original Kerberoast works. So you would request this using PowerShell, and you'd use Mimikatz, and then pull these out of memory, and then you'll go from there to crack them. Just Impacket makes that a little bit easier. So one of the questions we had was, so why can't we just use pcreds Wireshark? Okay, that sounds great. Let's just start ripping them off the wire. So it's actually not that simple. So the way it works is the service and the DC both know the service, or the account the service is running with, hence SPNs. So the user requesting the auth really doesn't need to know the user that it's running as. So that's actually going to be in the encrypted part of the ticket. So we can't actually just pull them off the wire, because how do we crack something if we don't know the username? And that username we'll talk about in a second, is actually going to be part of the salt that you use to crack the tickets. So now that we have auth, how do we actually go on cracking these tickets? Well, it turns out it's really not like typical password cracking goes. You don't just input a password, generate some stuff, and then try to see if they match. It turns out that the way it works, it's called known plain text attack. So if you think of the movie The Imitation Game, so throughout that entire movie, they had a series of messages, and all these messages had a known part in the message. So this was going to be the same in every single message, and that value was always going to be the same. So they knew every message coming in, so that's one less thing we have to try to brute force. Cracking Kerberos works the same way. There's always going to be the known part of the message that's not going to change, and we keep inputting keys, in this case passwords, until we try to decrypt the tickets and they're not garbage. So and this kind of goes into some other things that we're really not going to talk about. You can talk about pack validation, you can talk about gold and silver tickets. Not going to really discuss that. We've seen that discussed very well elsewhere, so we're not going to get into all of that. Okay, so if you ever run secret stump on a domain controller, one of the things we see besides the NTLMs is going to be this bottom half here, which I'm not sure if that's entirely readable, but is going to actually say Kerberos keys. So it turns out that NTLM and obviously LM hashes really aren't the only thing being stored within Active Directory password-wise. So really, how does NTLM work on a high level? So you give it your password, does some hashing, does some math, and then spits out that final hash. You can think of Kerberos keys more or less the same way. It's going to be that one-to-one where it's going to take the password, take the key, and then spit out the final value. So while they're not technically hashes, in this case, they can be treated as them as far as cracking goes. And as far as being keys, they can also be technically considered hashes. So what are these pre-shared keys actually? So it turns out that when you want to send tickets across the network, Kerberos is actually going to use symmetric key encryption to actually encrypt these tickets. So these pre-shared keys are actually going to be the keys on both sides that are used to actually encrypt those tickets. Now, as far as who knows the secrets, obviously the DC in the service will know what the authentication is, and then these are going to be created by the service, and then the DC will already know them. So you should always have a copy of these pre-shared keys to authenticate. So as far as generating these keys, they are going to be set based on the user's password. So there's a few things that'll come into play, but they essentially get updated on initial auth or a password change. And the thing we kind of found out a little bit, it's Microsoft, so you can't ever get 100% confirmation anywhere, but is really that the way it works is that the service is going to take the clear text, kind of encrypt it, send it over, and then the DC is going to decrypt the password. But really the important here is the DC will have your password in clear text for the short time. We know that because things like NIPS or Yellow Pages, it's going to have that clear text to generate those key files from there. And then same thing with the crypto. You really need that pre-shared, or your password in clear text to actually generate those pre-shared keys. So when we do start generating these keys, how does it really work? So it falls into two categories. So first is going to be a stream cipher, so that's going to be RC4, and that's going to take a bit of plain text at a time, encrypt it, and go all the way through the rest of it. And that's going to be your RC4/ARC4 as Microsoft named it. And then the next part is going to be your block ciphers. So this is going to be DAS, triple DAS, as well as both the AESs. And this is really going to take the block cipher, so it's going to take n bits of plain text at a time, encrypt that block, and then basically do that through the entirety of the plain text. But really that introduces your password is going to have to be either expanded or kind of rolled over to match the block size, so that the password is going to match the block. And then as part of AES, there's kind of really one overarching function here, and this is going to be string to key. So this is going to take your password and kind of start to generate those PSKs, those pre-shared keys. These is defined in MS-Kyle, kind of a Microsoft RFC file. That's really the only place we found it actually defined, but this kind of makes up the overarching part of generating these block ciphers. Now this function will be the same for all the block ciphers minus about a function or two from AES, which will make it more difficult to crack. But it's really made up of really only 4 parts here. So the first part, nfold, is again going to take that password to a fixed size. And then the PBK df2 function is really kind of the heart of AES. This is what's going to make AES more difficult to crack. This is going to take your password, the salt, and then the real part that makes it, again, more difficult to crack is going to be that it's going to put it through multi-rounds of the encryption. So it's not just doing it once, it's going to do it, it's going to be doing it 1,000 times. And then the last 2 parts here, the random to key is going to take that previous key, take a seed, make another key, and then the derived key right at the end is going to take that key and actually take a constant, and then again, we'll actually make that final key once more. So, so as part of that PBK function, AES kind of defines several things. Again, it's going to be the salt, so that's going to be the domain, and then username. You're going to take out the backslash. AES, both AESs are going to use 1,000 rounds of AES, and then that constant we were talking about earlier is going to actually be the word Kerberos. So that's not only defined in MS-Kyle, so you can actually see the screenshot out of the RFC there.
They literally take the key and mix it with the word Kerberos.
Yep. And the main reason we got, as far as the crypto goes, is the information's kind of all over the place. Impacket has some, Microsoft has some, and it's just kind of separated where everything is. We just kind of wanted to, again, like Jim said earlier, is bring all the material into one place as far as Kerberos goes.
If you've ever read Kerberos RFCs,
yeah,
you feel like you've returned from the Underworld, for sure.
Okay, so what do these keys actually look like? So the first part here is going to be your reversible. So this is when you select store the password using reversible encryption. More or less, the DC is going to take that password, do some reversible to it, and then basically start in the user parameters LDAP attribute for that account. It's going to be a binary blob. It takes a little bit to decrypt it. Obviously, NTLM and LM are going to be your typical hashes. And then the thing you really notice here is that RC4 is going to be the same as NTLM. So we'll talk about that in a minute. But essentially what the DC is going to do is not actually use that RC4 cipher. Even though it has it, it'll directly use your NTLM hash to kind of sign or to actually encrypt those RC4 tickets. The last 3 here is when you start to get into the salted ciphers, so it's going to be your DAS and both AESs, and then the last 2 really introduce that 1,000 rounds. It's not just doing it once, it's going to do the 1,000 rounds for each one of those. Okay, so now that we kind of know what they look like, where are they actually being used? So it turns out DAS is enabled on the DC, but it's not really used anywhere from what we can tell.
Stored on the DC.
Yeah, it's stored on the DC. RC4 is going to be used all over the place, and then AES is going to be used all over the place with more mixed results into what conditions. Okay. So going back to this screenshot here. So we kind of know what these keys are now, but why would the DC have all these ciphers or all these keys kind of already defined within the domain controller? So it turns out it's more of a fail-safe. So if the admins decide today we're turning on DES support, you don't have to go back for every user in the domain and say, change your password. So to generate these new keys. So the keys will already be there from when you changed your last password. So you're not going to have to change, again, everyone's password. So we thought, can we actually generate our own keys? And it turns out we actually could. So using one of the crypto libraries from Impacket, what we can actually do is kind of mimic what the domain controller is doing. So we can, again, feed it the username, the clear text password, like the DC is going to have, the domain, basically everything we need to create those keys. And we can actually start cranking those out just like anything like Impacket would see, or yeah, Secret Stump would see. So all the code for this is going to be on Echidna. So quick Greek history lesson, Echidna is also the mother of Kerberos, hence Kerberos, the three-headed dog. So just a little trivia there. So as far as really why this is interesting, so if in the future we do get tools that do really support Kerberos auth, we can import these keys and actually start minting tickets that way. But the real thing is we just want to see if we could do it. It's just research purposes. But that led kind of into the next thing is if we can generate them, we should be able to crack them too. Since again, they aren't going to be that known plain text, they're going to be treated more or less as hashes once again. So in the same repo, we kind of took the previous code, reversed it, and then we said, can we actually start cracking these keys? So we are able to. Now it's probably not worth dumping the entire domain's database trying to crack these. It is AES. It's gonna obviously take a lot longer than NTLM currently is. But it's more of a proof of concept cracker, and the thing it really alludes to is as far as the relative cracking speeds go. So again, what we kind of did was take the previous one, batch it out for the entire ciphers, and we said, okay, how long is it going to take to actually crack these keys? So if we don't have NTLM in the future, Microsoft actually does disable it, or we move away from it, whatever it be, how long is it actually going to take to crack? So the actual hash rate is not too entirely important. It was on a laptop VM, so super slow. But you can see here, as NTLM is about 56K, you drop to about 13K with DES, and then AES is really, again, obviously when you start dropping down to those double digits. So it gets down to about 20 and then about 11 hashes per second. So it's going to be significantly slower. So quick math here shows about a 5,000 times time increase moving from RC4 to AES pre-shared keys. And then again, this is going to be mostly due to those 1,000 rounds that PBK actually defines. The salts will come into play and kind of add a little overhead there. But just imagine going cracking tickets at about 4 hours, and then all of a sudden you jump up to about 20,000 hours. It's going to take a while. So there definitely is that benefit there. And then an interesting note here is DES we consider pretty terrible, but it's still slower to crack than NTLM is. So like the main question here is, can we really again move away from RC4?
Okay, so RC4 bad, AES pretty good, right? That's the lesson we take away from that. So if we can AES all the things, wouldn't that be amazing, right? So if you asked people who know about the Kerberoast attack, how would we influence what cipher is used within that attack. You get like a mixed results from your question. If you put Wireshark on a DC and just watched TGS reply tickets fly by all day, some of them would be AES and some of them would be RC4. So you might think, well, maybe the client has something to do with it. And it is true that the client, whenever it's talking to the DC, it does, in a very SSL-like way, say, hey, these are the ciphers that I support. Let's negotiate. And it negotiates with the server takes the client's list against the server's list and picks a cipher that they both communicate with. But it turns out that influencing this is not really up to the client. And we know this because we actually wrote a Kerberos client that could only talk AES. We would actually send the fact that we supported only AES encryption types, and we'd still get an RC4 encrypted ticket back from the DC. Yeah, real interesting. Really lobotomized the code there. But so it turns out that what that magic Kerberos ticket is ultimately the DC's decision. So let's take a look once again at the TGS rep ticket. And we see, okay, so we've got the reassembled Kerberos packet, because sometimes Kerberos tickets are big enough that they span multiple packets. And we've got this sub-element called TGS rep. That's the type of Kerberos, thing that's going on. Then we've got this ticket element, and then we've got this encrypted part, which tells you exactly what the ticket is encrypted with. So AES 256, and it's cipher 18, which is AES 256. And then this cipher section, which is a long bunch of gibberish, if you use invoke Kerberoast or get user SPNs from Impacket, this is the actual hash that you get out of a tool like that. So you can connect what you see in Wireshark to what you're seeing out of the tool. Okay? So just so we've established a way to analyze on, if we had Wireshark on the domain controller, we can analyze, okay, when are we seeing RC4 tickets and when are we seeing AES tickets? And this is basically how it breaks down. Okay? There's, by default, if you just set up a blank AD environment, this is when you see RC4 tickets being minted and when you see AES tickets being minted. Okay? So the first is if you're in a 2003 domain. Okay? Well, 2003 domain controllers can't support AES. The crypto was not introduced, so that makes sense. Okay? The next up is if you have, so remember SPNs, right? You can register a machine account or you can register a user account, right? So if you have a older machine, like a 2003 machine, registered in the SPN, right? So you're running the SQL server as the system account on a 2003 box, okay? And that's registered in the SPN. Then you get an RC4 ticket back. Okay, that's interesting. And it makes sense because the DC has to send a ticket from the DC to the client onto the service, and the service needs to be able to decrypt it, right? If it's a 2003 box, it doesn't have AES support. It won't be able to decrypt it, right? So maybe the DC knows something about that machine account. Okay. This third one is interesting, and everybody I've showed the slide deck, they've been confused by this one, but it turns out that Kerberos is really funny, and it lets you do some weird things. So an unjoined machine. So you can create a computer object in Active Directory, just like right-click, new computer, okay? And that computer has never touched, never joined, never seen a domain controller, right? It may not even exist, okay? Then you can also manually register an SPN for that computer account, okay? And then you can Kerberoast against it because the machine doesn't need to be up or even joined to the domain for you to be able to do it. And the DC says, I don't know what that thing supports because I've never talked to it, so I'm going to send it RC4. Okay? So that's an unjoined machine. That's a weird use case that you would hopefully never see in any environment. So this fourth one is a very common one in the environment. Once I explain it to you, you'll be like, oh, I see that all the time. Named accounts registered in the SPN. So this is like SQL SVC or administrator or, Bob is registered as the account running the SQL server, right? And he gets an RC4 ticket. That's weird. We'll talk about that one in a minute. And then the last use case is in a 2008 or later domain, with a 2008 or later machine registered in the SPN, you get an AES ticket, okay? Automatically. Because the DC says, hey, I support AES, he supports AES, I can send him an AES ticket, he'll be able to decrypt it, okay? And you see at the bottom, two different Wireshark packet captures of these various events showing the difference. Type 23 versus type 18. If you've ever seen type 23 and been like, what is 23 about? That's RC4. Okay, 18 is AES 256. Okay, so back to this named accounts thing, right? So if administrator is registered in the SPN, why does he get an RC4 ticket minted for him? And the reason is, if you think about it, the DC's job is to send a ticket that this account can decrypt. But the account administrator could be on dozens of machines across the environment, one of which might be a 2016 IAS service, one of which could be a 2003 Exchange server, which can't support AES and only supports RC4. You could also register an Apache web server running on Linux, and the DC says, I have no idea what crypto stack that thing's going to be using, right? So once again, the DC plays it safe and issues RC4. Okay. And with a machine account, it knows what crypto is possible because the machine tells its crypto capabilities when it joins the domain. There's actually an LDAP attribute. Okay, so how do we change this for normal accounts like administrator and Bob? Okay, how do we get it so that AES keys are used to encrypt the tickets? We see AES is better than RC4. We want to move to AES, right? And thanks to our friend Sean Metcalf and the people at Microsoft, they've given us this wonderful section of the account tab that allows you to check a couple boxes. It says AES 128 and 256 are supported on this account. So this is the account that the service is running as. Okay, so this is Bob or administrator or whatever your service account is. Service _ SQL 1. Does not require a reboot based on our testing. Depending on how XP in 2003 or older are in your environment, this may break authentication. So obviously, if you have an old environment, you wouldn't be doing this. Okay, so this is cool. We get AES tickets no matter what, as long as we've got our accounts configured this way. But this is like how I would have help desk update this information. What's actually happening on the back end? And it turns out there's an LDAP attribute, MSDS, supported encryption types. And this is an LDAP attribute within the service account. And if you set it to 24, you get AES 128, AES 256. Okay, how do you get the value 24 out of those two things? And it turns out that each cipher is associated with a hex value. So AES 128 and AES 256 are 08 and 10, respectively. You add 8 and 10 together, convert from hex to decimal, you get 18 to 24. And that's how you get the 24. So any combination of those values, you convert them to decimal, you put this number in the LDAP attribute, you've updated it for that account specifically. Okay. Okay, well that's interesting. I don't really want to sit there with an LDAP editor all day. How do I do this like in a way that's way better? And the way you do it is, of course, with PowerShell. Use a built-in AD commandlets, set AD user, the name of the service account that you want to update on, and then you replace the LDAP attribute with the value 24. Okay. There is a way to do this on every account across your domain. We are not putting that on the slide because we would like you to test this a little bit more, and so we didn't put that on the slide. So, okay, so that's interesting for blue teamers. This talk is about the future of red teaming, or as it relates to Kerberos. So, what does this mean if people start doing this in environments and we're pen testing these environments, right? And the result is desperate people, okay? We're going to start getting AES Kerberoast tickets, okay? And think about the AES cracking speed again. 4,000 to 5,000 times the speed. You're going to have to use a lot shorter password list and rule set in order to crack these AES tickets. But wait a minute. What happens when you actually try to Kerberoast AES currently? Right? What happens is tools give you an error message saying, error, encryption type 18. What do I do with that? I don't know what that is. That's crazy talk. Okay? So we went in and said into Impacket, and we could do it with invoke Kerberos 2. We said, let's not make that an error message. Let's actually strip that off and turn it into a ticket that can be cracked in a cracker. Okay? So this is a modification we did to get user SBNs as part of Impacket. We'll be submitting a pull request to the guys over at Core Security. And basically, you can take this ticket, and someday you'll be able to crack it, right? So Hashcat doesn't support cracking AES tickets yet, but at least we have something we can show the guys at Hashcat to be able to do AES Kerberoasting. So this is a new type of Kerberoasting. So that's cool. I can Kerberoast AES. Interesting. But if you were in the talk yesterday with the SpectreOps guys around Here Be Dragons, the ACL thing, they demoed something called Change NTLM in Mimikatz, right? And we sat in that presentation and we said, okay, and if you weren't in the presentation, basically how Change NTLM works is use Mimikatz, and let's say you've changed the password of a domain admin temporarily so that you can get access to a domain controller, right? And you want to set it back to what it was before, right? So the way that Mimikatz Change NTLM works is you take an NTLM hash from the history and you jam it back in to the Active Directory database, okay? So we sat in that presentation and we said, that kind of flies in the face of everything that we've seen around how the way that Kerberos keys are generated. So we went back to the hotel yesterday and did some hacking. And basically, because the reason it flies in the face is because the password is used to generate the Kerberos encryption keys, right? So when you are updating the Active Directory database and you don't have the password, what happens, right? So we thought one of two things happened. Either that we were wrong about the way the keys worked, I don't think that was that, or that we would see like old keys happen when we secret stumped. Well, it turns out with Microsoft there's always a third way, okay? So what we did was we set up an account to use AES only, okay? And we said so that it would have to use Kerberos keys, okay? It wouldn't use the NTLM hash, okay? We secret stumped to see what the Kerberos keys look like for that account. We said, okay, it has Kerberos keys. I know what they are, okay? And we Kerberoasted with our new version of Impacket that supports AES Kerberoasting. And we got a ticket back. Okay, so methodology validated so far. Okay, then we changed the password with Mimikatz Change NTLM and lobotomized the Active Directory database with a previous hash. And we were like, okay, let's secret stump again. Does it still have Kerberos keys? It didn't. It wipes out the Kerberos keys. That account no longer has Kerberos keys. So then we said, that's really weird. All it has is an NTLM hash in the Active Directory database. How does it do Kerberos authentication? Does it break Kerberos authentication? And what do you think? No, of course not. Because as my friend Michael McAtee says, no matter what, Active Directory will always authenticate. So the Active Directory database doesn't have Kerberos keys in which to encrypt tickets, but it does have an NTLM hash. And so what it does is, instead of using AES, which it's configured to do, it falls back to RC4. And you get an RC4 ticket, even though it's configured to use AES. So that was amazing to find that out. Really cool. Okay, so back to that was a cool digression. So the future of NTLM. So like, let's say, so in Kerberos, we have a way of turning off NTLM being used within Kerberos. But NTLM still used all over the network with like net NTLM challenge response authentication, right? How do we get rid of that? Well, it's possible that Microsoft could like rev NTLM authentication to do the same challenge response authentication, but instead of using the NTLM hash, they use the AES Kerberos key. Nothing, you know, they could rewrite Windows to do that, or they could just say, we're going to allow you to shut off NTLM authentication within your environment. That would be cool. It's going to be, even if they started on today, it's going to be a while before that's actually implemented. But imagine, right, a day when you dumped NTDS and you saw only Kerberos keys, salted Kerberos keys, so that the number of accounts that you dumped would actually, you know, increase the cracking time, you know, based on the number of accounts. It would change the Active Directory password game forever. It would be incredible. We also talked about how AES Kerberosting will still be possible, but it's going to be a lot slower to crack. In summary, I think we learned today RC4 is still used everywhere, but we have a way to fight it. AES Kerberosting going to be possible. And we also saw the difference between cracking AES versus cracking RC4. And we really know that we want to move towards AES because it is a lot slower to do that. And of course, to no surprise to anyone in here, NTLM really must die for password security to go up. So I want to thank you today for coming out. So our contact information, if you want to look at the code in Echidna, it's available on the Crow Center for Cybersecurity GitHub page. Thank you.